to Minfeng. Welcome to Idea Math, Pencil and Paper Math Talk Show, Episode 1.
Hi, my name is Yannick. I'm currently a junior from Trapezoid Academy.
Hi, my name is Vijay. I am currently a sophomore at Trapezoid.
And my name is Ivan. I'm currently instructor at Idea Math.
So we are going to open up our first talk show talking about math, and it's actually not the technical part about math. We don't want to limit ourselves to only the problem-solving techniques. We want rather about talking about how we develop thinking process and how to generate new ideas from old problems so we can get more out of the problem. Right? In a certain way, it's how we train our wonderful math team to get them better and better. Right? Those are wonderful members of our math team. So we prepared 7 problems this week, and we are going to explain those problems, and we will team up to explain the content of the problems. But I think rule number 1 is for the safety issue. We release these problems. We do encourage our students or parents to think about these problems, but they should never think about those problems while they are driving or doing something, cooking, all those things. They should, when they are watching TV or something, maybe they can think about those problems, right? Yeah. Safety is a big issue, right? When I was young, sometimes I think problems while I was driving. Now I think about it's really, really dangerous. That should never happen, right?
It's more dangerous than texting, right?
Oh yeah, definitely. So, who wants to explain problem 1, or what do we want on this problem?
I think I'll explain.
Okay.
Okay, so we have a 9x6 square, which I roughly draw as this 16. And we want to cut this piece of paper. Let's treat this as a piece of paper into a square. So apparently we want the size to be square root of 9 times 16 equals to 12. But the problem is how we're going to create this size.
So basically, we're cutting this rectangle into pieces.
Yes.
Yeah, we want to find the smallest number of pieces.
Yeah, as efficient as possible.
Because originally one of my students was thinking, well, I always at least can cut into 144 pieces. Right? That's clearly not what we want, right? And then some students will look at this and say, okay, I can make even 4 or 5 pieces and so on, right? And we will say, be more creative. There are even less pieces that you can do, right?
So we can aim for 2, 3 pieces. It should be possible.
I don't think 2 pieces will be actually possible because there are only that many ways to combine 2 pieces and it's really hard to make. Well, you can cut a 12 out of here, but
Yeah, you must start cutting as well from the rectangle, right? So you can pick a corner, pick 12, and start cutting probably under 90 degrees angle. You don't want to create fancy.
yeah, so you can make say 12 here. And cut it this way. So you have 4, 9. So we have 12 and we have something like the 3 by 12 region. So basically we want to make this into 6.
Right.
And that possible cuts.
Yeah. So there is a minimum number of pieces possible, right? And also very important, the minimum number of pieces does not mean minimum number of what? Cuts. That's very, very important. Because sometimes people confuse those two. They think minimum number of cuts means minimum number of pieces. But they are different concepts, right? They are different concepts. And of course, we were leaving this for you guys to think about. But this gives us a taste of our problems. What do they like? What are they going to look like? In the next week session, we will have a slightly harder version of this. So maybe what works for this week, the method, the 9 by 16 will not work for what? For next week's example. And then after that, we will give them another example about, based on this kind of idea, what kind of really hard problems can we ask, right? As a sequence, we try to develop our process of thinking, making the problems a little bit harder, and then, so we can learn more from this problem, okay? So who wants to do number 2?
I guess I can.
Okay.
All right, so for problem 2, this problem has 2 parts. First of all, we have an isosceles trapezoid. The question is to prove that these 2 base angles are equal in measure. So the definition of an isosceles trapezoid again is basically just a trapezoid where you have one pair of parallel sides, and these 2 legs are equal.
Why don't we mark that, so make it easier.
Yeah. So we have a situation like this. How do we prove that the 2 base angles are equal?
And then the second part is the converse of that statement, right? If I have 2 equal angles, is it necessarily true that the 2 sides are equal, right? So what is the things we really want to talk about here? What's the usual approach in many, many books that actually we have seen?
Well, I mean, whenever you have a trapezoid, usually it's a great technique to drop altitudes from these 2 vertices. So what we could do is
Wait, should we erase those 2 angles for now? And suppose we don't know that they're equal, right?
Right, so to try not to mislead our students, right, okay.
Right.
They are not, we are not,
We want them
we
to
want to show they are equal, yes.
So if we drop these 2 altitudes,
Uh-huh.
then now it looks like, well, from the definition of a trapezoid, these 2 are equal in length. And
Because in the middle, you actually have a what?
we have a rectangle.
Rectangle, right? Yeah.
So these 2 are equal in length, these 2 are also equal, and these 2 are both 90 degrees. So it seems like by just simple triangle congruence, these 2 have to be congruent.
Right.
By hypotenuse.
Hypotenuse length, which is actually based on Pythagorean theorem, right? So this is a common proof. We see actually many books even, right? But the key, the reason we put this problem over here is the core question. What's wrong with this proof? What's wrong with this so-called proof that appeared in many places, right? We don't want to pick hard geometry problems. We don't want to pick lots of hard problems to scare ourselves. Actually, it's start from easy problems, we can learn a lot, right?
And we can say not what's wrong, but something can be questionable in this.
Yeah, something questionable with this proof, right? Can you guys think about what is the question, what is the issue here, and how do you really fix this issue? And that's why we picked this topic for this week's book, right?
And then we have problem number 3.
Aha.
So we start with a quadrilateral that is inscribed with a circle. So let me draw a circle. We have a quadrilateral, and now is the diameter, because I know that the center O is here, and then I know that K and M are somewhere here. So my configuration is like this.
And then we have one more point. Km is equal to the intersect OL at P,
At P.
right? And then they give us some length. They give us length. OP is equal to,
This is 2, this is
I think this is 8.
8, and this is 18, and KP is equal to 9.
Right, and K is 18, right?
And we want to find the length MM. So
So what's the story? Why do we pick this problem?